you are falling, feet first, into the dark. And for the first few seconds, honestly, nothing feels wrong at all. So let me ask it straight. What would you actually see if you fell into a black hole? Not the movie version, not the screaming, the instant crush, the body snapping like a twig in the first frame. The real thing. Because what really happens is slower than that, stranger, and in a couple of places, genuinely more beautiful than any film has ever bothered to show you. What you would see down there breaks how you picture space and time, and even the idea of a single now. Stay with me, because there are about 6 things you would see, and each one is weirder than the last. Here is what you are actually falling toward. A black hole is not a hole. Drop that idea first. It is an object. A place where a huge amount of stuff got crushed into a tiny space, so tightly that its gravity curves back on itself and nothing can climb out. Not a rocket, not light, nothing. And we are not guessing at this anymore. We have photos. In 2019, a team pointed a planet-sized network of radio dishes called the Event Horizon Telescope at a galaxy named M87. They took the first real picture of one, a dark circle wrapped in a ring of fire. In 2022, they did it again, aimed this time at the giant sitting in the middle of our own galaxy. It is called Sagittarius A star, and it weighs about 4 million times as much as our sun. But how does something like that even get made? Nothing is just born that extreme. So here's the short version, and it starts with a star. Every star you have ever seen is a fight between 2 forces. Gravity wants to crush it. The heat from fusion pushes back. For most of a star's life, those 2 forces tie, and the star sits there, burning, stable, not going anywhere. But stars do not live forever. They run out of fuel. Our sun will burn for about 10 billion years. When it runs out, it will puff up, shed its outer layers, and settle down as a small hot corpse called a white dwarf. Quiet ending. But the sun is a middleweight. Go bigger. A star 8 or 20 or 40 times heavier than the sun, and the story changes. Those stars burn hot and fast. They live a few million years instead of billions, and when they run out of fuel, they do not go quietly. The fusion engine stops. The heat that was holding the star up against its own gravity just vanishes. So gravity wins. The entire star collapses inward. The outer layers fall, smash into the collapsing core, and rebound in a detonation that can outshine an entire galaxy for a week. That is a supernova, one of the most violent events in the universe. If you are anywhere nearby when it happens, the light alone is dangerous, but the core that caused all that does not get blown away. It keeps falling. If what is left is heavy enough, maybe 2 or 3 times the mass of the sun, it reaches a stopgap first. The crush gets so intense that protons and electrons fuse together into neutrons, and you get a neutron star, a ball of pure nuclear matter the size of a city, spinning hundreds of times a second, denser than anything else you can touch. Some of those are pulsars, sweeping the galaxy with beams of radiation like lighthouses. Those are weird, but they are still matter. You can in principle stand on one if you do not mind the gravity. If the core left behind is heavier than that, something more fundamental breaks. Neutrons resist being squeezed further because of one of the deepest rules in physics. No 2 particles can occupy the exact same state at the same time. It is why you do not fall through your chair right now. The electrons in your atoms and the atoms in the chair refuse to share the same space. That rule has a name, the Pauli exclusion principle, and under almost any condition in the universe, it holds. Neutron stars exist because even at the bottom of a supernova, neutrons still obey it. They push back. They refuse to share space. But if the core left behind is heavy enough, gravity does not care. The crush is so extreme that it overpowers even this. The neutrons stop resisting. They are forced into the same state, the same space, the same everything, and the last physical barrier in the universe simply gives way. There is no next stopgap, no force left in nature that can push back. The core collapses past every limit, past the point where matter has any structure at all, until all that mass is concentrated in a region so small that its gravity seals the space around it shut. Nothing, not even light, can climb out. That sealed off region is your black hole. That is your black hole. The corpse of a star that was too heavy to die any other way. Now, the one you are falling into is not one of those. Sagittarius, a star, the giant in the middle of our galaxy, weighs 4 million suns. No single star makes that. The stellar mass ones, the ones born from single supernovas, top out at maybe a few dozen times the mass of the sun. The giants are a different animal, and we are still figuring out how they form. Maybe they grew over billions of years by eating gas and stars and merging with other black holes. Maybe they started as giant clouds of gas that collapsed directly, skipping the star step entirely. Maybe they formed in the very first moments after the Big Bang, from dense pockets of energy that were already primed to collapse. We are not sure yet, but they sit in the middle of almost every galaxy we have looked at, like a drain at the center of a whirlpool, and they have been there since the galaxies were young. That is the thing under your feet. So what do you actually see on the way in? First, you would expect the obvious. You would expect to get yanked in fast, then crushed crushed the instant you arrive. Everybody pictures it that way. Clean, simple. And for a black hole this big, probably wrong. Because with a giant one like Sagittarius A star, you could cross the most important line in the whole thing and feel nothing at all at the moment you do it. No wall, no bang. We will get to why. But first you have to see the line itself. That line as a name. The event horizon. It is the point of no return. Think of it as the last edge where turning back is still allowed. Cross it. And to escape, you would have to travel faster than light, and nothing can do that. So nothing gets out. Here is the strange part. The horizon is not a solid surface. There is nothing there to touch. It is just a place in empty space where the rule quietly flips from you can still leave to you never can. And as you fall toward it, the first thing you notice is the light. The sky starts to bend. That black circle below you swells and climbs up around your view, and the stars near its edge do something impossible. They smear. They slide sideways. Light from stars that are actually behind the black hole gets bent around it and delivered to your eyes anyway. So you start seeing things that should be hidden. The whole starfield crowds and warps like you are looking through the bottom of a glass. And around the dark circle sits a thin, impossibly bright ring. The last light that looped the black hole one full time before it reached you. It is one of the most beautiful things a human eye would ever catch, and you would only have it for a moment, because now time itself starts to come apart. Here is where it gets genuinely hard to picture, so I will say it plainly. Gravity slows down time. The stronger the gravity, the slower a clock ticks. This is real, measured, boring textbook physics. It is called time dilation, which just means time running at different speeds in different places. Near a black hole, the pull is so extreme that the effect goes wild, and it splits into two stories at once. One for the people watching you, one for you. Watch the people first. Say a friend stayed behind, floating safely far away, filming you fall. From out there, they never actually see you cross the edge. Your fall looks like it slows down, and slows. Your image drifts to red, then dimmer, frozen just above the horizon like a photo fading in the sun. To them, you take forever to arrive. You basically hang there and go out like an ember. They never watch you fall in. Not really. Now you're side. From inside your own body, nothing about you slows down at all. Your watch ticks normally. Your heart beats normally. You fall in a matter of seconds. But when you look back up, out through that shrinking window of stars, the outside universe is speeding up. Stars wheel faster. The light from up there crowds into a tight, blazing circle above your head and shifts toward blue. The color light takes when it is racing at you. You are watching the sky above you run its clock fast while yours runs slow. Same fall. Two completely different truths about how long it took. Both of them correct, and you are still falling. Now the pulling starts. Not the crush people imagine. A stretch. Because gravity gets stronger the closer you are to the center, your feet are always a little nearer than your head, so your feet get pulled harder than your head. The difference tries to draw you out the long way, like taffy. Scientists gave this the least serious name in all of physics: Spaghettification. You get pulled into a thin string. Now, here is the catch that decides everything. On a small black hole, one just a few times heavier than the sun, this stretching turns deadly before you even reach the edge, and you are torn apart while the horizon is still ahead of you. Well, torn apart is polite. You are drawn into a strand of atoms. But on a giant like Sagittarius A star, the stretch near the edge is so gentle you would not even feel it. Which is the strange gift of the big ones. They let you in whole. So say you fell into the big one. You cross the event horizon. And this is the part that unsettles people the most. Nothing happens. There is no barrier, no flash, no click. You would not be able to point to the moment you pass the point of no return. You cross the most final line in the universe, and your body feels the same as it did a second before. You only know it happened because now every direction you could possibly move leads deeper in. Up is gone. The exits are gone. The center is now in your future, the same way tomorrow is. You cannot avoid it any more than you can refuse next week. Which leaves the last question, the real one. What is waiting at the bottom? And here is the honest answer. Nobody knows. This is not me dodging. This is the actual front edge of physics. Our best theory of gravity says all the mass collapses to a single point of zero size and endless density, called the singularity. And at that point, every equation we have stops giving real answers. It literally spits out infinity, which is math's way of saying the map ends here. So we cannot tell you what you would see in the final instant, because the rules we would use to predict it fall apart before you get there. And it is worse, or maybe better, than just not knowing. Physicists are actually arguing about the edge itself. One set of ideas built from the rules of the very small hints that the horizon might not be gentle after all, that instead of crossing quietly, you might hit a wall of blazing energy and be burned away right at the boundary. They call it the firewall. It clashes head-on with the calm crossing that Einstein's gravity predicts, and both cannot be true. That single fight over what a falling person would feel at the edge of a black hole is one of the deepest unsolved cracks in all of science. You falling in is not just a stunt. You are the experiment nobody can run. And once you are past the edge, the speculations begin. Because the truth is, nobody has been past the event horizon and come back to tell us about it. So physicists have ideas, not guesses, not daydreams. Mathematical structures that follow from the equations we trust, push to the place where the equations start breaking. Here is one. What if the singularity at the center is not actually a place where matter gets crushed to a point? What if it is a doorway? General relativity allows solutions where a black hole does not just dead end. It bends space so hard that two distant regions connect through a tunnel. You fall in one end and come out somewhere else. A wormhole, or to use the older name, an Einstein-Rosen bridge. The math works on paper. The problem is that the kind of wormhole the equations describe would collapse the instant anything tried to pass through it, including light. So you could not actually travel through one, not unless you had some way to prop it open from the inside, which would require a kind of matter we have never found and are not sure exists. But the idea itself does not go away. It is sitting there in the math. Here is another. What if the matter that falls into a black hole does not pile up at a single point at the center, but instead bounces? Not in our universe, in a new one. Some physicists have proposed that every black hole is a seed, that when matter collapses past the point of no return, it does not stop at a singularity. It rebounds, and the rebound creates a completely new universe on the other side, a baby universe. Ours, in this picture, might be the inside of a black hole in a larger universe, whose black holes are themselves spawning new ones, in a chain that goes who knows how far. We cannot test this. We may never be able to, but it is not fantasy. It follows from playing out the collapse fully inside the equations of general relativity. There is a stranger one still. Some physicists think the black hole is not hiding a singularity or a doorway or a baby universe. They think it is hiding the answer to a much more unsettling question. How does three-dimensional space actually store information? In this picture, the event horizon is not just a boundary. It is a surface that encodes everything that ever fell in, flattened like a hologram. All the information about every particle, every rock, every star that crossed the line, somehow smeared onto the two-dimensional skin of the hole. If that is true, then the interior of a black hole might not have a real inside at all. It might be a projection, and the unsettling part is that if the math works for a black hole, it might work for the entire universe. You, me, everything. A hologram projected from a surface we cannot see. None of these are confirmed. All of them are serious. They come from the same equations that predicted gravitational waves a century before we measured them, and black holes themselves decades before we photographed one. The math has been right before about things that sounded ridiculous. It might be right again about something stranger. So let me walk you back down, slowly, one last time. You fell feet first into the dark. The stars bent and smeared around a circle of pure black. A thin ring of light burned at its edge, brighter than anything you had ever seen. Behind you, the whole outside universe crowded into a shrinking blue window and ran its clock fast, while yours ran slow. And your watching friends saw you freeze and fade and never arrive. You crossed the last line and felt nothing. And what waited past it is a place our smartest people still cannot agree on, still cannot see, still cannot solve. You would not go out with a scream. You would go out with a question nobody up here has ever been able to answer.